Some of the strangest planets we've found shouldn't exist for more than a heartbeat of cosmic time, yet there they are, orbiting peacefully, as if the laws of physics were negotiable. For 3 decades, extreme exoplanets have been quietly rewriting our textbooks. Every time we thought we understood how planets form, or what normal looks like in a solar system, a new discovery arrived and basically said, "Nice theory, here's reality." And that's the real power of these worlds. Hot Jupiters, super-Earths, rogue planets, lava worlds with rock vapor atmospheres, each of them is a controlled experiment that nature is running for us, under conditions we never imagined. By comparing these alien systems to our own, we're starting to answer some big questions. How flexible is planet formation? How fragile is habitability? And where exactly are the real limits of what nature can build? Let's start with a basic assumption that turned out to be wrong. For most of the 20th century, planetary scientists quietly believed that our solar system was typical. Small, rocky planets in the inner region, giant gassy planets farther out, icy leftovers beyond that. This arrangement wasn't just neat, it arose naturally from the nebula hypothesis. In this model, planets form from a disk of gas and dust spinning around a young star. Close to the star, temperatures in the disk soar above several hundred degrees Celsius, hot enough that volatile materials like water, carbon dioxide, and methane remain as gas. Only metals and silicate rocks can condense into solid grains. Farther out, beyond what's called the snow line or frost line, often a few astronomical units from a sun-like star, temperatures drop low enough, maybe below 150 Kelvin, that water and other ices can freeze. Inside the snow line, rocky worlds. Outside it, icy cores that can grow big enough to grab massive hydrogen-helium envelopes and become gas giants. Simple, elegant, and apparently confirmed by our own backyard. Then, in 1995, we found a Jupiter-sized planet orbiting just 7 million kilometers from its star, a distance where temperatures can exceed 1,000 degrees Celsius, a gas giant deep inside the snow line. This was 51 Pegasi b, the first known hot Jupiter, a planet that our models said shouldn't have formed where we found it. This forced a fundamental shift. Planet formation, it turns out, is not a local phenomenon. Planets migrate. In a protoplanetary disk, you don't have a serene carousel of particles. You have a viscous, turbulent plasma and dust ocean with pressure gradients, spiral density waves, and magnetic fields all interacting. As a newborn planet orbits within this disk, its gravity raises spiral waves in the gas, like a ship generating wakes. Those waves carry angular momentum away from the planet or toward it, depending on which side of the orbit they form more strongly. The end result is what we call disk-driven migration. In some regimes, known as Type 1 or Type 2 migration, a planet can exchange angular momentum with the gas so efficiently that it spirals inward, sometimes by several astronomical units, in less than a million years. That's a tiny fraction of a star's lifetime. Hot Jupiters are probably exiles. They formed beyond the snow line, where solid cores can grow quickly, and then were dragged inward by the disk or by later gravitational encounters with sibling planets, until tidal forces from the star finally stopped them. This single class of extreme planets, hot Jupiters, has already taught us that a planet's current address is not where it necessarily grew up. To reconstruct a planet's true origin story, we have to model not just where it is, but how violently its orbit may have evolved. But hot Jupiters did something else. They exposed how biased our early theories were by one data point: our own solar system. Once detection methods improved, especially transit surveys like Kepler and TESS, we discovered that the most common kind of planet in our galaxy isn't anything like Earth, or Jupiter, or Neptune. It's something in between. We call them super-Earths and mini-Neptunes, with radii roughly 1.3 to 3 times Earth's, and masses up to about 10 Earth masses. These worlds are ubiquitous around other stars, yet they're completely absent from our solar system. That's like surveying hundreds of cities and realizing that the most common type of building in the world is something that literally doesn't exist in your hometown. This raises a brutal question. Are we the weird ones? In many exoplanet systems, These super-Earths and mini-Neptunes orbit extremely close to their stars. Some complete an orbit in just a few days. Their densities, which we infer by combining transit radii with radial velocity masses, are all over the map. Some are dense, probably rocky, with large iron cores. Others are puffier, consistent with a rocky or icy core wrapped in a hydrogen-helium envelope or a supercritical water layer. This diversity tells us that the line between rocky terrestrial planet and gas giant isn't sharp. It's more like a continuum, where a few Earth masses can make the difference between a world with a thin, breathable atmosphere and one with a thick, crushing envelope that turns the surface into a high-pressure, superheated ocean, or a mantle of exotic ices that don't behave like anything on Earth. And that has direct consequences for habitability. We used to imagine a narrow Goldilocks zone, a band around a star where the temperature would allow liquid water to exist on a rocky surface. But what our extreme exoplanets show is that temperature is just one variable in a much larger phase space. Take ultra-hot Jupiters. At temperatures of 2000 to 3000 Kelvin, molecules like water or methane can be ripped apart on the day side, leading to atmospheres dominated by atomic species and ions. At these temperatures, exotic chemistry emerges. We detect molecules like titanium oxide and vanadium oxide, which act like high-altitude absorbers and can create thermal inversions, stratosphere-like layers where temperature increases with height. These planets are uninhabitable in any conventional sense, but they're laboratories for atmospheric physics under extreme radiation. They help us test how molecules break, recombine, and transport energy when subjected to conditions that are hard to simulate on Earth. The same radiative transfer equations, the same fluid dynamics, and the same chemical reaction networks apply, scaled down appropriately, to more temperate worlds. Understanding how atmospheres handle energy at 2500 Kelvin sharpens our tools for interpreting atmospheres at 300 Kelvin. Then there are lava worlds, like 55 Cancri or K2-141b. These planets orbit so close to their stars that their surfaces are likely oceans of molten rock. On the day side, silicate materials vaporize into a rock vapor atmosphere. On the night side, that vapor can condense and literally rain stone back into the magma ocean. It's a rock cycle, running in hours instead of millions of years. Extreme temperature contrasts and tidal locking teach us about atmospheric circulation under one-sided heating. Hot gas rises on the day side, flows to the night side, cools, sinks, and returns as a warped version of our own planet's Hadley cells, jet streams, and heat engines. When we push general circulation models to handle these alien regimes, we're also stress testing them for more Earth-like scenarios. Exoplanets with eccentric orbits, stronger stellar flares, or dense CO2 atmospheres. Even the strangest orbits matter. We've found planets on extremely eccentric paths, where their distance from the star might vary by a factor of 10 or more during each orbit. That means their incident stellar flux can swing by roughly a factor of 100, since flux drops with the square of distance. Imagine a world where seasons are not caused by axial tilt, like on Earth, but by wildly varying distance from the star. A global climate that repeatedly bakes and freezes on orbital timescales. These are natural experiments in climate resilience. How quickly can an atmosphere radiate away heat? Can an ocean store enough thermal energy to buffer these swings? Does a thick greenhouse layer stabilize conditions or drive runaway feedbacks in atmospheric collapse?